Morning guys, we're doing what it says on the tin here, inclined planes where any external forces are parallel to the plane. What I mean by external forces, if you have an object on an incline or on a plane, there are two forces automatically acting which are not external. One is the weight of the object and the other is the normal reaction between the object and the incline or the plane. But there will be occasions where there are other forces acting, so somebody's pushing or pulling something up an incline. They would be called external forces, and in this section we're only looking at those forces that act parallel to the plane. So here we have an object in contact with an inclined plane, and I mentioned two forces that are acting which are not external forces. One is the weight of the object acting vertically downwards, and the other is the reaction force, sometimes called the normal reaction force. Normal, you will remember, a line that is a normal is at 90 degrees to something. So the normal reaction is the reaction force which is at 90 degrees to the plane. When we are looking at motion on a plane, we want to resolve the forces parallel and perpendicular to it. Now, by definition, as I said, the reaction force is already perpendicular to the plane, so we don't need to do anything with the reaction force. But for the weight component, we need to resolve it parallel and perpendicular to the plane. So, to find our resolved forces, we draw, as you may remember, lines perpendicular and parallel at the start and at the end. Now, if we have alpha as our angle between the horizontal and the incline, this angle here would be 90 minus alpha, which means this angle here must be alpha again. So consequently, the component into the plane is 5g cos alpha, and the component down the plane is 5g sine alpha. Here's another example. We've got the weight perpendicular to the plane and parallel to the plane. So our two components, and alpha would be that angle there. So into the plane it's w cos alpha, and down the plane it's w sine alpha. And you can remember that because the weight component parallel to the plane is always sine, so it's sine down the incline. Okay. Now, if the inclined plane is smooth, the weight component down the plane will cause the object to accelerate, and that's because in the direction parallel to the plane there are no other forces. There's no push or pull force, there's no friction force, so that weight component will see the object just slide down the incline. In this example then, we have a block of 10 kilograms sliding down a smooth plane inclined at 15 degrees to the horizontal. So the forces on that block, straight away we can always put the weight on. Remember, if the mass is 10 kilograms, the weight is 10g newtons. The block is in contact with an inclined plane, so there is a normal reaction force at 90 degrees to that plane. The incline is smooth, so there's no friction acting, and there's no push or pull force, so those are the only forces acting on the object. Here in part B, we want to calculate the magnitude of the normal reaction on the block. And what we want to do, we want to resolve that weight component, the weight into its two components, into the plane and parallel to the plane. So we mark our two components on. The size of the component into the plane is 10g cos 15 degrees, and down the incline it's 10g sine down the incline. We can then, when we've marked those components on, we can remove the weight, and our force diagram now looks like that. Now, that little notation you can see there is my shorthand for perpendicular, i.e. perpendicular to the plane. And because we're working perpendicular, I'm just going to remove for the moment the 10g sine 15 degrees because that's acting parallel to the plane. Now, perpendicular to the plane, the object is not accelerating into the plane and it's not accelerating away from the plane, which means those two forces must be in equilibrium. They're cancelling each other out. Therefore, R must equal 10g cos 15, and that's 94.7 newtons. For part C, we want the acceleration of the block. Therefore, I'm only looking at forces parallel to the plane, so I'm going to remove the normal reaction and the weight component into the plane. Now that's my notation there to tell you that I'm working parallel to the plane, and the only force we have parallel to the plane is the 10g sine 15 degrees. It is that force that is producing the acceleration. So using force equals mass times acceleration, 10g sine 15 equals 10, which is the mass times the acceleration, dividing both sides by 10 gives me an acceleration of 2.54 meters per second squared. Here in example 2, similar to the previous one, except this time we have a pull force up the incline of 30 newtons. Marking all the forces then on the mass, the first one we might mark on would be the weight, 5g newtons. The mass is in contact with the incline, so there's a normal reaction. And finally, there's the pull force of 30 newtons up the incline. For part B, find the normal reaction. Once again, we resolve the weight into its two components, into the plane and parallel to the plane. Marking on the two components, remember, why is that 25 degrees there? Because that's 25 degrees, so in this right angle triangle, this will be 90 minus 25, and therefore that must be the 25. So it's 5g cos 25 into the plane and 5g sine 25 down the plane. We can therefore see that working perpendicular to the plane and removing the two parallel forces for the time being, the object is not accelerating away from the plane, nor is it accelerating into the plane, so R must equal 5g cos 25, and that's 44.4 newtons. Now in part C, find the acceleration of the object. Once again, we're working parallel to the plane. That's my notation for parallel. So we can remove the perpendicular forces, and we have two forces left, the 30 newtons pulling up and the 5g sine 25, which is the weight component, down the incline. So if we use resultant force equals mass times acceleration, then 30 minus 5g sine 25, that's the resultant force, equals the mass 5 times the acceleration a. And if we divide both sides by 5, we find that the acceleration is 1.86 meters per second squared. Well, I hope you've understood those two examples and the principles involved. If you then turn to exercise 5b, questions 1, 2, 3 and 5. Best wishes, I hope they go well for you.